In this lecture, we're going to cover the theory of Big Bang nucleosynthesis. All right, first I'm going to ask three questions. They are, what does Big Bang nucleosynthesis mean to you? So I'm abbreviating Big Bang nucleosynthesis with BBN. What physics do we need to consider? And what are the main actors? And go ahead and pause the video here and give an answer to these three questions. And once you're done, come back. Okay, so now I'm going to provide some answers to these questions. So what does Big Bang nucleosynthesis mean to you? So for some of you, this, you might say, it's the synthesis of nuclei at high temperature. This is associated with Big Bang. And maybe this is nucleosynthesis in the high entropy regime. Maybe some of these are the answers that came to you. But one thing I really want to emphasize is that this Big Bang nucleosynthesis is really the process of freeze out. We're going to start out with free neutrons and protons and consider all the possible interactions during a certain time period. And as the universe expands and cools, we're going to be looking at freeze out. In particular, Big Bang nucleosynthesis will predict that roughly 70% of the universe is hydrogen and 30% is helium. And there's trace amounts of everything else. So helium forms from freeze out. So that's one thing I really would like you to remember about Big Bang nucleosynthesis, is that it's really about freeze out of nuclei from the individual constituents of them. All right. So what physics might be relevant? Well, we're going to be looking at a little bit of statistical mechanics. E&M is certainly important. We're talking about nuclei, so probably the strong force, but it turns out it's really the residual strong force that's relevant. And we're talking about interactions within the nucleus, and so the weak force is relevant as well. Now, what about the actors? Well, there are many possible actors. Some include neutrinos, neutrons, protons, electrons, positrons, and then maybe some mediators like photons, W, Z boson. We're eventually going to form nuclei, so maybe helium-3, heavy hydrogen or deuterium, helium-4, lithium, beryllium. And these are all possible important actors. So what we're going to do in developing this theory of Big Bang nucleosynthesis is we're going to first focus on these because they set the stage. So first, focus on these because they set the stage for producing the light nuclei on the periodic table of elements. So first these to set the stage for these. Okay. And in particular, we're going to focus on three possible interactions between the neutron and the proton. So first of all, the neutron can capture an electron type neutrino. It'll produce a proton and an electron. Now this reaction can go in this direction as well. The proton can capture an electron to produce a neutron, an electron type neutrino. Here's another interaction that's important. The neutron can capture a positron and it will produce a proton and an anti-electron type neutrino. And then once again, this reaction can go in both directions. And then here's the third that we're going to consider in setting the stage. We can have a neutron decaying into a proton, but we need to conserve charge, and we're going to conserve lepton number with a neutrino. So we have an anti-electron type neutrino. And once again, this reaction can go in this direction as well. Now, the energies of these reactions is important. So there's an important, we notice that here, the energy of the electron minus the energy of the neutrino is going to equal Q, where Q is the difference in the rest mass energy of the neutron and the proton. C squared, and this is equal to 1.293 MeV, just to give you a scale for this. So this difference in the neutron and proton is equal to the difference in the energy of the electron and energy of the neutrino. And so those energies obviously include rest mass plus, the momentum component of that. For this middle one, we have that the neutrino energy minus the electron energy is equal to Q this time. And in this last one, we have that the energy of the electron and the energy of the neutrino is equal to Q. Now, for high temperature and density, these processes go in both directions. In other words, they are in equilibrium. We're going to use that a little bit later to find an algebraic expression. And we're going to use this. One may derive the fraction of neutrons at any given time or temperature. Let me just put capital T. Or temperature. At some point, these reactions will freeze out. We won't be able to have these reactions anymore. And at that freeze out, after this freeze out, the number of free neutrons at freeze out determines the helium-4 composition of the universe. And we're going to find that the mass fraction of helium is roughly 30%. Just from working out the physics of freeze out of neutrons of these three interactions that we have up here. In order to get to this, we're going to need to calculate the rate of neutrons going to protons via all three channels. Now in Weinberg represents the rate of going from neutrons to protons in all three channels with this equation. I'm going to write down or this integral. I'm going to write down this integral, and then we're going to see where this integral comes from. Okay, so first I'm just going to write it down. A times integral of 1 minus me squared over q plus little q squared to the 1/2. I haven't even defined what little q is yet. I'm just going to write it down first. And then we have capital Q plus little q, q squared, dq, all over 1 plus exponential of minus mu over kT, where that's mu is the chemical potential. And then 1 plus exponential of q plus little q divided by kT. Now, this seems like a complicated integral. Why did we write it down in such a way? It's really in the, by writing it down in this way, we're able to incorporate all three of these rates of going from neutrons to protons into one integral expression for the rate of going from neutrons to protons. And it's that mathematical trickery that is useful in calculating these rates. Okay, so once again, this integral represents the rate of neutrons to protons via all three channels. All right, and this A is a constant that represents, these are all weak interactions here, and these three equations, those are all weak interactions. And so A is a constant that represents the weak interactions. I'm not gonna, so here is the weak interaction constant squared, 1 plus 3 GA squared cosine theta C divided by 2 pi h bar, 2 pi cubed h bar. Now, I'm not gonna, this is not a nuclear physics course, so I'm not gonna go into the details of where each of these terms come from. They all have their own interesting aspects. I'll just say that A represents the scale or the strength of the weak interaction. And you can look up what each of these are on your own. For the purpose of this class and the purpose of this math, now this integral will go from minus infinity to infinity, but it turns out that there are three regions of this integral that represent each three of these equations or rates or channels. And so when we integrate from minus infinity to minus q minus MEC squared, that represents one of the equations. We do minus q to minus MEC squared to minus q plus MEC squared, that represents another equation. And then when we go from minus q plus MEC squared to infinity, that represents the third channel or the third equation. And so in this way, this one integral, by taking the integral from minus infinity to infinity, represents all three channels through this funny parameter called q. Okay, so let's figure out what is this? What was Weinberg? Why did Weinberg do this? How was Weinberg able to do this? To write down this this rate in one compact form. So we're gonna do this. Let's do one example. Instead of doing all three, we'll just do one example. To derive this rate of going from neutrons to protons. Okay, and we'll take this one. We'll go from n plus the positron goes to a proton plus the anti-electron type neutrino. Okay. So the cross section for this interaction, the cross section for this interaction is 2 pi h bar cubed times the same A constant. So it gives us the scale of the weak interaction. And then the energy of the neutrino squared divided by the velocity of this lepton. And in this case, it happens to be the positron. All right, the other thing that we need to consider is we need to consider the number density of the lepton. In this case, it's the positron. And so I'm going to say the number density of this positron is PE, where that's momentum, and it's a function of temperature. So it's a function of these two things. This is equal to 4 pi PE squared dPe over 2 pi h bar cubed, and then times this 1 over exponential factor because we're dealing with fermions. Exponential, and then the energy of the electron divided by kT plus 1. All right, that represents the number density of these leptons, in this case positrons. Okay, so now we're looking at this equation, and we see that we're going to capture a positron onto the neutron that produces a proton, and then it's going to produce a neutrino. Now, this reaction can only happen if all of the states for the neutrinos are not occupied. If all of the states are occupied, then if all the quantum states are occupied, then you can't fill those states, and this reaction can't happen. And so this is called blocking. And so we need to estimate what is the blocking for this reaction. So in other words, if there are very few neutrinos in the possible states, you're likely going to have this reaction. However, if most of the states for the end state neutrino have been occupied, then it's unlikely that this reaction will go forward. So we need to consider the fraction of unoccupied states for the anti-electron type neutrino. So let's first consider fraction of occupied states. And once again, the reason we're doing this is the ability for this reaction to proceed is proportional to the fraction of unoccupied states. If the fraction of unoccupied states is 0, then this is not going to happen. There are no unoccupied states because we're dealing with fermions. You cannot have more than one fermion in each of the states. Okay, so let's first consider the fraction of occupied states. That is, for a fermion, the fraction of occupied states is 1 over the exponential of E nu divided by kT plus 1. This is equal to the fraction of occupied states, F0. I'm going to call it F0. Now, the fraction of occupied states plus the fraction of unoccupied states is equal to 1. All right, so now we have that the fraction of unoccupied states is equal to 1 minus FO. Therefore, FU, after a little bit of algebra, is equal to 1 over exponential of minus E nu kT plus 1. So this is similar to the fraction of occupied states, except there's a minus sign in the exponential that's in the bottom. And if I recommend that you pause the video here if you'd like to derive, just to make sure that that is true. Okay. Now, let's calculate the rate. The rate of this reaction happening, a neutron capturing a positron, producing a proton, plus a neutrino that's electron type and has to be anti to balance this equation. This rate is equal to, well, it's proportional to the number density of the positrons, is proportional to the cross section, the velocity of interactions for the positron, and then this will only occur for the fraction of unoccupied states that are available. And we're going to integrate this over all of the possible momenta. Okay, remember this density that we wrote up here is in terms like per momentum interval. Okay. So now we have expressions for each of these, the density, the cross section, the velocity, and FU. And if we plug this in, we get A, and we're going to integrate the momentum from 0 to infinity. Then we have E nu squared, PE squared times 1 over exponential E energy of the electron divided by KT plus 1. And then that came from the from NE. And then we have the fraction of unoccupied states, which is 1 over exponential, oops, let's do parentheses here. So minus E nu divided by KT plus 1. And then dPe. Okay. So what we did is we took our density NE, plugged it into here, the cross section, VE, and then FU, and we end up with this integral here, and we're integrating over all possible momenta for the lepton, which in this case is a positron. Okay, now here comes the trick. We're gonna rewrite this. We're gonna do some variable substitution so that we can rewrite this, and then we'll have a similar form for each of the 3 equations. So if we let Q equal minus the energy of the neutrino, and for this particular reaction, the minus the energy of the neutrino is equal to minus Q, and then minus the energy of the lepton. All right, this is the variable substitution that we're going to do. Now, it may not seem obvious to you. It's like, okay, fine. How's that going to work? It will lead to a form of this that when you do a similar variable substitution for all 3 equations, you see the same type of integral. In fact, the integral that we wrote up above. And I'm just going to work through doing this variable substitution for this one particular case for one of these equations. All right, so now let's go ahead and square Q. So Q squared is equal to the neutrino energy squared, right? We have the neutrino energy squared up here, so that's why we did that. We wanted to find Q squared. And we have that this is another expression that will be useful in the substitution. If we rearrange this, we have Q, little q plus capital Q squared is equal to the energy of the lepton squared, in this case as a positron. Okay, so now we've done this variable substitution of Q, which apparently is related to energies. All right, we're going to be integrating over Q instead of momentum. So we need to find dq in terms of PE. So if you would like to pause here and work this out yourself, feel free to do that. And now we'll compare to what I have found. So dq is -1/2 PE squared. So that's momentum plus ME squared to the -1/2. So that's the total energy of the lepton times 2 PE dPe. And the 2's cancel. The 2 and the 1/2 cancel. All right, and so we have, if we rearrange, we have that PE squared dPe, which is what appears in the integral equation up above. Up here we have PE squared and then dPe. So rearranging this here, PE squared times dPe is equal to minus Q, capital Q, plus little q squared dq times 1 minus me squared. I'm obviously leaving off a c squared there, divided by little q plus capital Q squared, and all of that to the 1/2. Now that may seem like, okay, it's not, it wouldn't be obvious at first glance that replacing PE squared dPe with this mess on the right-hand side would get you anywhere. But once again, the reason we're doing this is when we make this substitution in each of these equations, we get the same integral, but with different limits. Okay, so let's go ahead and plug that back in. And now we have that the rate of going from neutrons or protons for this particular reaction, so plus a positron gives us a proton plus an electron times neutrino is equal to a integral q squared times q plus little q squared times 1 minus me squared divided by little q plus capital Q squared to the 1/2. And then we have dq integrating over this new variable. And then we have two exponentials in the bottom. 1 plus exponential q divided by kt. And then times 1 plus exponential of capital Q plus little q divided by kt. All right, so now we have this expression, and if everything is done right, it should look just like this one up here. Okay. All right, so now that we have that expression, now we need to see what is this expression in terms of, or what are the limits of integration for this? Well, we were integrating PE from 0 to infinity. Okay. Now, recall that we need to figure out what are the limits of integration for Q. Recall that Q is equal to minus E nu is equal to minus Q minus E little e, the energy of the lepton or positron. Now, when the momentum is equal to infinity of this lepton or the positron, then Q goes to minus infinity. So up here, if the momentum is infinity, then E sub little e is infinity, and we go Q is minus infinity. And if PE is equal to 0, then Q goes to minus Q and then minus MEC squared. And so those are our new limits of integration. We're going from minus infinity to minus Q minus MEC squared. All right, and so now we see that this integral of this specific form integrated over these specific bounds here gives us our rate for that one equation. And if we want the rates for the other equations, we just need to add those other two. And it turns out you get the same integral, but slightly different integration bounds. So for the other two, we have the same integral, there we go, same integral, but different bounds. Such that integrating Q from minus infinity to infinity captures all three rates. Okay. All right. So now moving along. So these are the rates. To figure out what is the mass fraction of neutrons in the universe, we need to solve a rate equation. So the time derivative of the mass fraction of neutrons, so the mass fraction of neutrons is x sub n, and the time derivative d by dt is equal to, well, is going to be equal to minus the rate of neutrons leaving. So that's lambda n to p times the number of neutrons you start with. But this also increases by the rate of protons going into neutrons times the mass fraction of protons. So this is our balance of neutrons. And we didn't derive the rate equation from going from protons to neutrons. It's very similar to what we did with one slight but important difference, and we'll get to that in a second. But it's just basically looking at the same equations and going in the opposite direction. And going in opposite direction, what you notice that instead of, so the way I've written these equations here, and here, and here, we're starting off with the baryon that has a higher mass going to a baryon with a lower mass on the right-hand side. And so that's going down in energy. And if you go in the backward direction, you're going up in energy. You're going from the baryon with lower mass to baryons higher mass. And that is the main difference in the rates in going the other direction. It's, in fact, the same equation, so very similar, but going the opposite direction, you're going up in energy instead of down in energy. We're going to, let's recall that the total mass fraction of neutrons plus the mass fraction of protons equals 1. All right. Therefore, we can rewrite dx of n by dt is equal to minus lambda going from N to P times the mass fraction of neutrons plus lambda going from P to N times 1 minus Xn. I'm taking this equation and just saying that XP is equal to 1 minus Xn. And then we're going to plug that into here. All right, now in equilibrium, the rates of these going both ways is roughly equal. So dxn by dt is roughly equal to 0. And this suggests that the rate of going from N to P times Xn is equal to the rate of P to N times XP. Now we have the ratio of, by this, we have that the ratio of the rate going to P to N divided by the ratio of N to P is equal to the ratio of Xn to XP. And by the Saha equation, this is equal to EXP of minus Q KT. So the fraction of Xn to XP is equal to the exponential of minus Q over KT. I'll remind you that Q is equal to Mn minus Mp times C squared. And that concludes the first part of our introduction into the theory of Big Bang nucleosynthesis. In the next lecture, we will be exploring what does this mean. We'll be evaluating this at different timescales and temperatures to figure out when does freeze out happen and what's the value of Xn at the time of freeze out, because that's a really important parameter that will tell us, it sets the stage and tells us how many helium particles there will be in the universe.